All right, so now we're going to take a look at integrals formally. All right, so there are two main branches in calculus. There's differential calculus, which has been the majority of this course, and then there's integral calculus. All right, so integral calculus is related to area and volume, which we've already been looking at, but now we're going to look at it with this new integral notation, okay? So here's how it works. So if we think of some function, and we start approximating it in terms of areas, right? So areas of rectangles in this case. So you can see, so this is the sum. So if we start with one rectangle and went up to 8, the length and the width, so the width would be, the distance from here to here. Your length is your height of your function, okay? Then as we grow, so you can see now this is 30. So we've got 30 rectangles. That's a lot closer approximation than 8 would have been. We don't have all these gaps, right? So we're getting closer and closer to the approximation. So what happens if we go all the way to infinity? Well, then we have the area under the curve, okay? And instead of using, the length, what we can say is f of x, okay? Because that would be the height at any point on that function. And so we say from 1 to infinity, and then dx. So dx, what that is that's an infinitesimally small change in x. Okay, so it's the same as like change in x, like delta x, but but this is as we're getting like infinitesimally small, right? So they're getting closer and closer, so you can't even make the distance out between them anymore because it's that small. And for reference, this is the same x like as when we wrote like dy dx. It actually is that too, right? It's like change in y over change in x, and again, it's like a very, very small change in x. So it is that this is the same dx that we have seen in the past. All right, so instead of sigma notation, so that was this was sigma notation. Integrals use this notation. So we're going to look at first an indefinite integral. So I'll explain that here in a minute. But for now, let's just think about like what an integral is. So this symbol is called the integral sign, and it is an elongated s for sum. And then it would be of the function, and then you end it with dx. Okay, and then that gives you the sum of the area under the curve. Okay. So as an example, if this was our function, and we want to find the area under the curve for this function, we could write it like this, okay? But now this would be the area like for the entire function. So that'd be the area under the curve for the entire function. So that's why this is an indefinite integral, it's not defined. It's not from a certain x value to another x value like we were doing in the last lesson. It's just in total. So that's called an indefinite integral. So we're given a table of common indefinite integrals. This should look pretty familiar. These really are our antiderivatives, right? So you can see that we've got, so in general, the x to the power of n. This is just we add 1 to the exponent and then multiply by 1 over that plus c. So yeah, same thing. It's actually the same table that you've probably seen before, just in a different notation.